Chapter 8 goes over weathering, which creates soil, and also can contribute to mass movement, which we generally refer to as landslides, but as we'll see, that is not an accurate geological term. So when we look at the external processes that happen on Earth's surface, we're going to have a different point of view than what we saw when we've been looking at the internal processes, like volcanoes and earthquakes and plate tectonics, and even as we were looking at mountain building. Weathering, mass movements, and erosion are external processes because they occur at or near the surface. They are powered by gravity as well as energy from the sun. And as we know, these types of processes are integral parts of the rock cycle, because we know that rocks must be broken down and decomposed so that we can go through our different phases in the rock cycle, especially looking at the sedimentation part of the rock cycle. Now, some parts of our surface we know from the past couple of chapters are elevated by the processes of mountain building, which we refer to as orogeny, as well as volcanic activity that is, steadily cranking out magma to create plutons and batholiths. So those are referred to as internal processes, and their energy comes from Earth's interior instead of gravity and the sun. And at the same time, as these are going on, opposing external processes, those that are happening at the surface, are continually breaking the rock apart and bringing it, to the debris to lower elevations, which could potentially get incorporated into those internal processes if they get deeper, into the lithosphere or asthenosphere. So the three types we're going to look at, and really in this chapter, we're going to focus on weathering and mass wasting or mass movement, and we'll look at erosion in chapter 10, which will be the next chapter that we look at. So weathering is the physical breakdown, which is the disintegration, and the chemical alteration or decomposition of material, again, at or near the surface, because we're talking about external processes. Mass wasting or mass movement is when rock material, including soil and really anything that gets in its way, are moved downslope due to gravity. And there's usually going to be some triggering source for this, and we'll look at those. And then erosion is the physical removal and transport by some mobile agent, and that's water, wind, or ice. And like I said, we'll get to that later on. Now we'll watch a video that shows how these three processes have influenced the structure of the Grand Canyon.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at the role of mass wasting in creating the Grand Canyon. After watching the video, you should be able to break down the respective roles of rivers and mass wasting in producing canyons. So take a look over this scene. This is a classic looking Western canyon. Beautiful example of a river flowing down in the bottom of the canyon, and then these cliffs and plateaus that rise up above it. Naturally enough, you might think, okay, the river carved this thing, and the river is the dominant force in being responsible for making this landscape feature, but mass wasting has a huge role to play. Take a look at this canyon for a comparison. This is a slot canyon. It's called the Narrows in Zion National Park, and basically it's a really narrow canyon. And this is the Virgin River here. that down in the foreground that has carved the narrows. Why do the narrows look so different from that canyon that we just looked at? Some rivers are wide, some rivers are narrow, some rivers have wide spots and narrow spots. Narrow spots are a really good place to put dams because you have to build a lot less dam to span the river. So what's the deal here? Well, it's something like this. Take a look at the Grand Canyon here. We've got a photograph and you can see the Colorado River running through it, and you can see the north and the south rims over there in the far distance, the plateaus that the canyon is cut into. The sketch here in the lower left basically shows what we're looking at. You can see there's sedimentary layers and metamorphic and igneous rocks in the inner gorge, all carved by the Colorado River, right? Well, sort of. Really what the river does is it's responsible for removing material in its bottom. So it scours into the rock underneath it and removes that material. That means that you end up getting one of those slot canyons, kind of like the Narrows in Zion National Park. But having big steep cliffs that are thousands of feet tall are not geologically stable. So you end up getting landslides that basically take the material on the sides and drop it down into the river bottom. And once that material ends up in the river bottom, the river can cart it away, but mass wasting ends up taking it from the high areas and dropping it down to the low areas. So landslide by landslide, the Grand Canyon has been widened. So what does that mean for the Narrows at Zion National Park? What would you predict for the future of this scene? Well, over time, these sandstone cliffs are going to collapse downward. Hopefully that woman won't be standing there when this happens, but these are dramatically oversteepened, and they will indeed fall in eventually. And underneath this sandstone layer is a weaker layer, a shale, and when that shale is cut into by the Virgin River, it's going to undermine the sandstone in a very big way, and this canyon is going to widen rapidly. In fact, most of Zion National Park is a widened canyon where that process has already taken place. Good job. Thanks for your attention. This has been another Smart Figure.
So as you saw in the video, we had some weathering, some erosion, some mass movements that formed the Grand Canyon with the way it looks now. And, you know, the Grand Canyon never looks the same day to day because all of these processes are still continuing. They're still carrying on. So let's take a look now at weathering. So weathering is, again, basic part of the rock cycle. So it's a key component when we look at all of the different processes that take place in the earth as a system. Many of the minerals and elements that we find in soil, which we'll talk about here in just a few minutes, were freed from solid rock by these weathering processes. And as we're going to see, contributes to some of Earth's most beautiful and most spectacular scenery. So all materials, regardless of what they are subject to weathering. And there are two types. When it's fragmented, mechanically fragmented, which is disintegrated, or when it is chemically altered or decomposed. So mechanical weathering includes physical forces that will break rock into smaller and smaller pieces without changing its chemical composition. So it's just like you had, you know, a hammer and a rock, and you're just breaking this rock into smaller pieces. You're not changing any of the composition of the rock. You're just changing its physical appearance by making it, you know, one big rock into several smaller rocks. Chemical weathering, on the other hand, or decomposition, is when we are actually chemically altering the rock. Think about it this way. If you had a piece of wood and you had an axe and you chopped that wood into little pieces, that would be the equivalent of mechanical weathering. It's still a log. It's still the same type of tree, the same type of wood. You just broke it into smaller pieces. But if you put that into a fireplace and burn it, now you have chemically transformed it. It is not wood anymore. Now you've got ash, which is just carbon. And so that's the difference between mechanical weathering and chemical weathering. Physical changing versus chemical changing. Now we have a couple of other smart figure videos that we're going to watch here about weathering.
This video shows the creation of an arch, such as the ones in Utah's Arches National Park. Weathering processes are key to the formation of these unique landscape features.
So looking at delicate arch, which I have been to arches in Utah and seeing all the arches there, the window arch, and there's delicate arch, and there's so many beautiful arches. And one of the ones that we saw when we were there several years ago has since collapsed. But when you look at delicate arch, I want to point out a couple of things. You know, in our last video, last chapter 7, we looked at, you know, joints and faults. And when you look at delicate arch here, you can definitely see some fracturing here. You can see these joints very clearly in this delicate arch. And then, you know, if you kind of look beyond this, you can see actually right back here a little fault where there has been a little bit of slippage on either side of that, as well as some other joints. And as we're going to see, as we have more and more joints that form in the surface of these rocks, that can lead to more mechanical weathering as well as chemical weathering.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to define and distinguish physical and chemical weathering. So things fall apart. That's the sort of point with weathering. And this is an example of that, a non-geological example, a bicycle that's rusting after it's been left outside. So you start off with bicycle and atmosphere, add a little bit of rain and repeated cycles of wetting and drying, and you end up with something new, this substance called rust. So rust is an example of chemical weathering, basically where a chemical reaction takes place and a new substance is produced. You can contrast that with this scene outside of Moab, Utah, where the Entrada sandstone has been broken up into a series of fins. Basically, it's been fractured multiple times, and those fractures are an example of physical weathering, basically taking one solid chunk of something and breaking it into smaller pieces of that same substance. So this started off as one continuous sheet of sandstone. Now it's been broken into many individual pieces of sandstone, but they're still sandstone. Physical weathering and chemical weathering end up aiding and abetting one another. In other words, they help one another out. And that's what's illustrated here in this picture. So basically, by taking this initial cube of rock and then breaking it into a greater number of pieces, in other words, the same volume of rock, the same mass of rock, but a greater number of pieces, we've physically weathered it here, we've ended up increasing the surface area. And that is really important because it's on the surface of the rock that chemical weathering does its work. Just like it's on the surface of the bicycle where the rust accumulates, it's the same thing with rocks. As they're being chemically weathered, they don't get weathered from the inside out. The chemical weathering starts on the outside and works its way in. So the example over on the far right here is going to be much more susceptible to chemical weathering because it's already been so pervasively shattered, broken up by physical weathering. Okay, so let's see if you can distinguish here whether this is an example of physical or chemical weathering. There's some water in a little bottle here. You put it in the freezer, and then the water expands, and it has shattered the bottle. Physical or chemical weathering? You make the call. Okay, so hopefully you said physical weathering, and that would be correct. Okay, so the bottle is being shattered here into a bunch of little shards of glass. So it's still glass. There's no new substance that's been produced. It's just breaking an initial substance, glass, into a smaller number of pieces. Good work and good luck. Thanks a lot for your attention. This has been another Smart Figure.
So you saw there some examples of mechanical weathering. And when we have mechanical weathering, as we're having this one large rock and it's breaking into many smaller pieces, like you saw in the video, this also increases its susceptibility to chemical weathering. So there are four main processes that lead to mechanical weathering. So we have frost wedging, sheeting, salt crystal growth, and biological activity. So first is frost wedging. And as you saw in the video, when we have that bottle of water and we freeze it, we know that the glass can shatter. Water expands as it freezes. So frost wedging is when water works its way down into the cracks or the fractures within the rock, and it freezes, and then as it's expanding while it's freezing, it's pushing those rocks apart, continue cracking and fracturing that rock until eventually they break off. Frost wedging can also occur in a different way. This has been fairly recently, within the past 15 years or so, that this has been discovered. So, and this was studied in soils first. When soils that contain a lot of water freeze, they expand due to the growth of those ice crystals. Okay, that makes sense. But those masses of ice crystals grow larger because they're supplied with unfrozen water that's, coming up from the groundwater, or that's, running underground that is still liquid. And as more water accumulates there and freezes, the soil is moved upward. The same thing, or a very similar process, happens with within the cracks and spaces of rocks. Those ice crystals continue to grow larger as water comes into them from surrounding pores. And as these ice masses continue to grow, that weakens the rock, causing it to fracture. We also have the growth of salt crystals. So rocky shorelines, as well as arid or kind of dry areas, have or are the best place where we see this. Sea spray, so we're talking about salt water from the ocean. Sea spray or salty groundwater gets into the crevices or pores in rocks, and the water will evaporate, leaving the salt behind. Those salt crystals grow larger as more water comes in and evaporates, and as those salt crystals grow, they again weaken the rocks and push them apart. And this causes the fracturing and causes the mechanical weathering. We also can see this on roadways, not around here because we don't have a lot of snow and ice in the winter, but up north where they use salt on the roads to melt the snow and the ice, it dissolves in the water, gets into the cracks, the water evaporates, the salt crystals push apart the the cement and the asphalt in the pavement, and so it leads to those cracks that you see. Another process is called sheeting. Sheeting is when we get essentially these layers of rock. This occurs when large masses of igneous rocks, particularly granite, are exposed by erosion. And instead of just small fragments coming off, whole sheets will get loose and begin to break off. And the reason this happens is because of a reduction in pressure. When the overlying rock is eroded away, that's called unloading. And as that overburden is removed, the granite starts to expand and separate from the rock body, and we get these whole sheets that are peeling off, creating what we refer to as exfoliation domes. And we'll look at a video of this. Human activities can also cause sheeting, and we can see this in mines and quarries. Fractures can also be caused when igneous material cool, or in tectonic forces due to mountain building. And then let us not forget biological activity, plants, burrowing animals, and humans, of course. Plant roots, when they're in search of minerals and waters, they can grow into fractures in the rock, and as the roots grow, they push those rocks apart, leading to mechanical weathering. And also, organisms play a lot of roles in chemical weathering as well. So now we're going to look at a couple more smart figures on frost wedging and also sheeting.
Hi, this is Callan Bentley. Welcome back for another smart figure. In this video, we're going to take a look at ice wedging. And after watching the video, you should be able to describe what ice wedging is, why it happens, and its effect on rocks. So let's begin our discussion with this iconic landmark. This is the Old Man in the Mountain. It's in New Hampshire, or I should say it was in New Hampshire. This sort of craggy looking face over here. So the idea is that this looks like a face to some people. That face basically broke off and dropped off the mountain at some point in recent history. And because it dropped off the mountain, New Hampshire lost a vital symbol, but we can take advantage of this because this offers a great lesson in geology. So the basic idea here is the idea of ice wedging. The way ice wedging works is that water expands in volume by 9% when it turns from water into ice. So 9% increase in volume means that the ice basically pushes outward on any sort of container that it's housed in, and that can cause that container to break. So here's a non-geological example, a bottle shattering when the water inside freezes. And you may have experienced this yourself if you ever put a bottle of some beverage into the freezer and then it froze before you had a chance to drink it. Well, the same thing applies to rocks. So high up in the mountains, water gets into little fractures in the rocks. As that water freezes, it pushes outward on those fractures. So it basically enlarges the volume of the fracture, and that can actually serve to make the fracture propagate. So the little tip of the fracture will propagate out and the fracture will get longer, but it will also widen the fracture, and that can cause blocks of rock to go tumbling over the edge. So this happening every winter, tumbling blocks of rock down, you can see that this big giant pile of rock has built up at the base of the mountain. So here's the source for those sediments up here on the mountain cliff, but they end up piling up down below on what's called a talus slope. So this talus slope it's made out of boulders that are derived from the cliffs up above it. Now, can that same principle be applied to anything besides ice? Hopefully, the picture here prompted you to say yes. Obviously, tree roots can also penetrate into fractures in rock. And as those tree roots grow, it's not the same as freezing, but they end up basically exerting an outward pressure on that fracture, and that can cause blocks of rock, like this one here, to be popped off the face of that cliff. So root wedging works in much the same way as ice wedging. Both are vital forms of physical weathering. So where does that leave us with the Old Man in the Mountain? Well, that craggy profile that we looked at earlier is actually a function of ice wedging, and the breakdown of that profile was also a function of ice wedging. This was a feature that was both created and destroyed by the same process, ice wedging. Thank you so much for your attention. Hello, this is Callan Bentley. Welcome back for another smart figure. In this video, we're going to take a look at the phenomenon of sheeting and discover how it forms and what its consequences are. So let's begin our discussion by taking a look at the iconic landmark called Half Dome. This is in Yosemite National Park in California. Basically, there's two things at work here. First off, let's note the scale. There are people here climbing a ladder to give us a sense of scale. Part of Half Dome, basically everything to the right of that line, has been removed by glacial action, and we'll talk about that perhaps in the glacier chapter. However, what we want to focus on right now is this sort of onion skin looking feature here, these flakes that seem to be coming off, and they're all parallel to the sides of this dome, or half a dome. So what's going on here is that Half Dome is made out of granite. Granite, as you know, is an intrusive igneous rock and forms deep underground, so it forms under confining pressure. So there's basically pressure on that magma chamber at the time it intrudes into the crust, and then it crystallizes into igneous rock. So crystals form and it becomes one of these big blobs of igneous rock that we call a pluton. Now, if later on that pluton is brought up to the surface of the Earth, the pressure on it has been released. And as a result of that pressure being released, it actually expands outwards in all directions. So the relief of the pressure basically causes it to increase in volume very slightly. And that increase in volume is actually greater than the strength of the rock. And so the rock tends to break in a series of fractures that are basically perpendicular to the expansion direction. So if it's expanding in all directions, you end up getting this onion skin-like pattern of flakiness on the outside of that pluton. So when you go to Yosemite National Park, you're going to see this just about everywhere you look. You might hike up to view a waterfall, but look beyond the waterfall and you can see all these parallel fractures of rock. These are examples of sheeting. All right, let's quiz you real quick. Which of these two types of rock, intrusive igneous rocks or extrusive igneous rocks, are going to be most likely to experience sheeting when they're exposed at the surface? Hopefully you said the intrusive igneous rocks because they form deep underground under confining pressure. The extrusive igneous rocks wouldn't work because they form at the Earth's surface, so there's no reason for them to expand when they're exposed at the Earth's surface. It's only the intrusive igneous rocks that basically form at depth and then will expand when they're brought to the surface. So an example of an intrusive igneous rock would be a granite.
So now we'll turn our attention to chemical weathering. So breaking rock into the smaller pieces as we do with mechanical weathering aids in chemical weathering by increasing the surface area that's available for attack. So it basically, as you saw, is going to increase the surface area where chemicals can get in there. And chemical weathering also contributes to mechanical weathering because as the chemicals come in, it weakens the outer portions of the rocks, which then can allow them to be fractured or broken. So as we look at chemical weathering, we'll see that water and carbonic acid are going to be our two major sources of chemical weathering. Water, by far the most important agent. Pure water, non-reactive, but water is able to dissolve a lot of different substances. And so when we put these dissolved materials in there, it essentially activates this chemical weathering power of water. One thing that can be dissolved in water is oxygen, which will oxidize some materials. If you expose iron, like an iron nail, to oxygen, it will rust. And if you have rocks that have iron-rich minerals, they oxidize. So this is an example of chemical weathering. Carbonic acid occurs when carbon dioxide dissolves in water. Rain acquires carbon dioxide as it falls to the atmosphere, picks up more from the decaying organic matter as it goes through the soil. And carbonic acid will form two very reactive compounds, the hydrogen ion and the bicarbonate ion. And these are what really lead to the breakdown in rocks. It can decompose several different minerals, produce products that are water soluble. Calcite, which we find in limestone and marble, can be attacked by carbonic acid and can be broken down into different components. Now, spheroidal weathering is a very interesting process. Spheroidal weathering occurs as a result of mechanical and chemical weathering that turns rocks into these spherical structures or spheroids, and that's where we get that term. Weathering, the way it attacks the rock faces and the rock corners, means that those experience a little bit more weathering than the other surfaces, and that starts to lead them to get into this spherical shape. And so we'll watch a short video on that.
Hello there, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at spheroidal weathering. And after you're done watching the video, you should be able to describe what spheroidal weathering is, what it looks like, and how it forms. Here's a look at a scene you might encounter if you ever visited Joshua Tree National Park in Southern California. There in the Mojave Desert, you'll find a granite that has been broken along a series of fractures. So we would call these fractures joints, perhaps. And these joints divide the granite up into a series of angular blocks. So you can see that these blocks, for instance, over here on the upper left, they have sort of a diamond shape overall. But not all of them have that shape. For instance, over here in the upper right, you see some that have sort of a rounded form. In the foreground, there's two very nice boulders that have a very rounded shape to them. And up here at the top, you can see there's one that's almost perfectly spherical. So what's going on with this? How do we explain this disparity between really angular blocks of granite and really round ones? Well, it goes back to what we were discussing in another Smart Figure, that basically the increase in surface area of rock due to physical weathering ends up producing more area for chemical weathering to attack. So let's go ahead and just zoom in here on the first block in this diagram. You'll notice that this block is a cube of rock, not quite a diamond like the ones we were just looking at, but close enough. And it's got 6 faces. The corners basically have the greatest amount of surface area of any of the faces on the block. So that basically they're exposed on the top, the left, and the back, if you want to think about it that way. And that's more area for chemical weathering to attack. So what that means is that the corners are going to tend to wear away faster than the rest of the rock. So we're going to eat away at these corners more rapidly than we would eat away, say, at the middle of these faces. So how does that relate to the scene we looked at in Joshua Tree? Well, it'd be something like this. You've got an initial situation where you have granite. That granite is being physically weathered, so it's being broken into a smaller number of pieces. Those are the angular blocks. Then weathering goes to work on those angular blocks, transforming the ones with really sharp corners into increasingly rounded shapes. And then basically that's exposed at the surface, and that's the scene that we were looking at. So the overall trend here is basically to go from an initial angular block of a greater volume and then wearing away the corners more rapidly, and after the corners, the edges more rapidly. And over time, that'll basically reduce that initial cube into something that is increasingly spherical. So the end result basically is a sphere, and a sphere is the most efficient shape in terms of surface area to volume. So it's got the least amount of surface area for a given volume of rock. Now, is spheroidal weathering the only way that you can produce a rounded boulder like this? Hopefully you answered no. This will be a concept that we cover in the next chapter, but you can produce a rounded shape also by basically tumbling an initial angular block downstream or over and over in a surf, and you basically will break off the little pointy bits that poke out, and you'll get a rounded shape that way.
Now, when we look at weathering, weathering doesn't occur uniformly over different masses of rock. So it's very ununiform. And so this leads to what we call differential weathering, which is caused by variations in the composition of rock. And it creates some pretty unusual landforms that we might not expect. So other factors that influence the type and rate of rock weathering are the characteristics of rock as well as the climate. So rock characteristics include their mineral composition and solubility, as well as joints or fractures that we see in the rocks that can lead to, more mechanical and chemical weathering. On page 242, you have a picture of a couple of different headstones, one of granite and one of marble. And what we see is that granite can withstand more of this weathering than calcite can. So that can make a difference, as well as climate, particularly temperature and precipitation. The frequency of the freeze-thaw cycles can affect the amount of frost wedging that takes place. Temperature and precipitation also exert an influence on chemical weathering and what types of plants or vegetation that are present. So human activities can also influence the rate of chemical weathering, as can, warmer temperatures and an increased presentation. So now we're going to take a mobile field trip to New Mexico and look at some of the unusual rock formations that have occurred due to differential weathering, like this particular one here.
Hello, I'm Michael Collier. Rocks don't last forever. They break down, they weather at the Earth's surface. That's the misty Badlands down there. It's a moonscape in northwest New Mexico. It's a great place to get a bird's eye view of rocks being sculpted by weathering. On this field trip, we're going to look at strata that were deposited during the time of the dinosaurs. Different layers within these sedimentary rocks weather away at different rates. The result is this wild collection of unexpected shapes. We'll learn that weathering is caused by mechanical or chemical forces. Water, fire, even human beings can hasten the processes of weathering.
The Bisti lies 30 miles south of Farmington in the heart of the San Juan Basin. These 75 square miles of the Fruitland and Kirtland formations are filleted open, mostly by water, sometimes by wind, exposing 70-million-year-old sedimentary rocks, sandstones, shale, and mudstones. During the late Cretaceous, an inland sea occupied this part of North America. Rivers and deltas on the edge of the seaway were home to fish, turtles, crocodiles, and early mammals. How many of those animals do you think you would recognize today? The Fruitland Formation is riddled with fossilized bones as well as petrified wood. The overlying Kirtland Formation is busting its buttons with dinosaur remains. Now, as layers of the Bisti are peeled back, bones are exposed. In fact, a new species of Tyrannosaurus was excavated here not long ago. The Bisti Badlands sit 6,000 feet above sea level. Winter nights are cold, but there's plenty of sunlight to raise daytime temperatures. Any water that creeps into rock crevices repeatedly freezes and thaws, expands and causes cracking in a process called frost wedging. Blocks are pried into smaller, angular pieces, a type of mechanical weathering. When minerals that form deep underground become exposed at the surface, they must adjust to new conditions of lower pressure and temperature. Exposed to the sun, or soaking in the rain, rocks begin to disintegrate. Feldspar crystals decompose into clay. Quartz crystals break down into grains of sand. The Bisti is a stark desert, but a few springs do flow here periodically. Salts can be dissolved in the water and then deposited into crevices. As salt crystals grow, they enlarge cracks in the rock and, like freezing water, break it apart. Also, chemical weathering is greatly accelerated by the presence of acid in groundwater. This might happen when rain mixes with carbon dioxide from the atmosphere to form carbonic acid, or when minerals like pyrite decay into sulfuric acid. Can you think of other examples of acid hastening weathering? The Fruitland Formation is a stack of hard and soft layers, sandstones on top of shale, mudstones on top of coal. Sometimes a strangely shaped hoodoo forms when a cap of sandstone shields the underlying shale from rain. In this way, sandstone and shale, crumbling at different rates, exhibit differential weathering. Weathering and erosion are separate processes. Weathering breaks rocks down. Then erosion, powered by water or wind, carries grains away. But the two can be intertwined. As erosion carries away particles of rock, fresh exposures are subject to renewed weathering. A surprising variety of agents cause weathering. Animals can be prodigious burrowers, busting rocks apart as they dig. Fire is another agent. The Fruitland Formation is riddled with coal seams, some of which burned while still underground. Nearby layers of siltstone were baked and broken into red clinkers. In the last few hundred years, humans have become significant agents of weathering. It's true that the Bisti Badlands are a protected wilderness, but by conservative estimates, the Fruitland contains 90 million tons of coal, a fact not lost on power companies who would burn it to generate electricity. When miners dig up the coal, they also cause weathering. Can you think of other human activities that might influence weathering on a geologic scale?
So as you can see with weathering, we have mechanical and chemical weathering, and now you can see all of the different types of rock formations and what happens when we apply these external processes. So in the next video, we'll pick up with the rest of Chapter 8. We'll take a look at soils and those mass movements that are commonly referred to as landslides.